Hi, this is Dr. Joe Chow speaking. Today, I would like to talk about this NDA and Bio5B2 drug with PAMPA dissolution. Okay, this PAMPA dissolution is a new instrumentation which will help us in NDA and Bio5B2 drug oral drug development. And let's check from here. From my background first, I had worked in Sandoz and Pfizer for about total 10 years in the United States, and also worked for New Jersey Institute of Tech for 5 years as an adjunct professor. In those years in pharmaceutical industry, I have filed about 60 NDA drug, and now I have around 10 customer global wise for formulation development as a partnership. And from this PPT, as you can see, the drug absorbed orally can be really figuring out through the right side chart. As you can see, the drug can be absorbed through a small intestine length L, which indicated the drug comes from left side through L to the right side, can be figuring out based on mass balance, which is equation number 1. So as you can see, from left side is Q times C0, which is the mass rate, and the right side, exit side is Q times Cm, which is the mass rate out, and whatever comes in minus comes out, the difference is absorbed. So because of the drug is mass balanced. So then we can write an equation like this: drug absorbed F equal Q times 0 minus Cm, which is like left side minus right side equals absorbed. So by integrating this equation 1, we can end up with equation 2, which gives us F equal JW times A. JW is the wall flux, and A is the absorption area of small intestine. So further, scientists figure out that JW is really equal CB times PE. CB is the drug concentration, and PE is the permeation. So by substituting these 3 into 2, that gives us this equation, which is drug absorbed equal F equal CB times PE times A. So the CB is really the drug dissolution, and PE is the drug permeation, and that A is surface area of small intestine. So interestingly, if you compare with 1995 for the BCS classification, you can see there are really 2 parameters. One is PE, one is CB, and that happened to be included in the equation here in the oral drug absorption, which is CB times PE times A. By tradition, these CB and PE were measured separately if you develop a new drug. However, in terms of this definition for the CB and PE, they are really interrelated. So the CB and PE should be measured simultaneously. But I mean, back in 1990, there is no such simultaneous instrumentation invented until 2020. We invent this PAMPA dissolution, and literally these CB and PE can be simultaneously measured and be able to see the drug formulation performance, right? So this validated equation, is quite useful in designing this PAMPA dissolution, because what's really is dissolution side can help us figuring out the CB, and the PAMPA side is really help us figure out the PE. So, it can be determined nowadays with this PAMPA dissolution. Let's talk about this PAMPA first. Due to this KCO2 measurement, there's some difficulties. First is that we had to incubate this live cell of KCO2 in the laboratory for about 20 to 30 days before you can use. The second problem is its reproducibility is not good. So scientists try to find out a way that can be used in laboratory, therefore come up with this chemical membrane called PAMPA. And the PAMPA really is designed like the graph here shown. If you have dissolution, with API, the API is going to be permeate through the PAMPA and being collected and measured in the absorption side. And these API, once that they try to permeate through these membrane, there is a layer called UWL, which is unstirred water layer. They are existing on both sides of PAMPA. So the stagnant-wise, the thickness is 1500 nanometer. However, the real intestine is about 100 to 300 nanometer. Therefore, both sides of solution need to be stirred in order to mimic the human intestine thickness. Okay, that's what the whole idea transform from KCO2 to PAMPA, and therefore it can be measured in the laboratory. In addition to the PE, we have CB to be really need to be mimic to the GI tract of human, and therefore the left side graph indicating the time versus pH along GI tract. So as you can see, this pH initially in the stomach is about 1.5 or so, and then within about 30 minutes increase to about pH 6.5. That's why we design initial fasting state simulated gastric fluid for 400 ml within first 30 minutes. And after that, we will add concentrated fasting state in intestinal fluid to becomes like pH 6.5 eventually, okay? That mimic the GI tract pH plus media, okay? So in addition to this like 400 plus 100 configuration, you can do the 250 ml also for the low dosage drug, okay? Now, however, usually we will use paddle or basket with that RPM range. And the last one is such a barrier media really can be purchased from this website, okay? It's really commercialized today. Okay, now let's come back to this PAMPA dissolution. What's the configuration shows here is that the upper side is 6 vessels of dissolution. And correspondingly, you will have PAMPA dissolution, PAMPA apparatus. And in between, they are connected with the pump. So whatever the drug dissolved in dissolution will be pumped to the PAMPA side to be permeate and collected through these fiber optics. So same as this dissolution side. So data from this dissolution side for CB and permeation side for PE are all like simultaneously collected through fiber optics and into the PC data recording, okay? So based on these, then the design can be really applied because they are mimic this human intestinal fluid plus the PAMPA design, right? Okay, so data of comparison between the PAMPA and KCO2 indicate as following. We have 6 drugs, the hydrochlorothiazide, bosentan, telmisartan, izetamib, etoricoxib, and amlodipine. And as you can see, F means drug absorbed, CB means drug concentration area is the PAMPA permeation area. So with these, we can calculate based on the F equals CB times PE times A. We can calculate the PE easily, right? So the PE here is calculated based on these upper 3 numbers and becomes like 6.8, 10 to the minus 7. This KCO2 value reported by such article is 4.8 to the 10 to the minus 7. Okay, so that's for SCT. Similarly, calculation can be done for the other 5 drugs, and data comparison indicated they are fairly close, to these KCO2 permeation for the same drug. Okay, that indicated that PAMPA can be really employed in the laboratory instead of KCO2, because if you prefer PAMPA, it takes only like maybe less than 10 minutes, everything's done. And however, if you try to use KCO2, it's like 20 to 30 days preparation. Okay, and data indicated here, as we can see from my previous presentation as a YouTube base for this graph. Okay, here we will state it quickly is that this is the case for bioequivalence prediction, meaning for generic drug. And here we have 2 cases. One is telmisartan 40 milligram. The other case is 80 milligram for the bosentan. And you can see the red line represent the brand, blue line represent the generic. And they are fairly close in permeation. However, for the bosentan side, these red and blue, they are fairly close. However, the third second generic is from T Pharma is really not catch up with permeation. So, such a system can really be used in generic drug development if your formulation does not really show good permeation, right? Compared to the brand drug. Then we can use this system to adjust the formulation and matching with the brand permeation. Okay, so in addition to this generic drug demonstration, now let's come back to this NDA formulation with PAMPA. As you can see from this graph, from this upper graph, it shows the NDA process, right? And what's interesting is that this PAMPA dissolution introduced to help this preclinical to clinical in a way that we initially need the PAD simulation that's required by FDA. So once we are done with this PAD simulation, which we will describe in later PPT to have a reference for demonstration how we end up with this PAD simulation. Okay, once you've done the simulation, you will have fairly reliable PK data generated. With this PK data generated for your NDA, then you can compare that with previously approved ADME database from FDA, because the similar PK data will indicate you will have similar block curve. So with that similar PK, you can have your IOD selected, right? So once you have your IOD oral drug IOD selected, then you can perform PAMPA dissolution. That will give you a curve of permeation from your dosage as your IOD for your NDA. With this curve, then you can start your formulation, the drug formulation. So once you compare with your IOD, then you can easily finish your drug formulation. Then with that, then you can proceed this phase 1. And through the phase 1, phase 2, then you can also make modification, for your formulation and end up with final PK and PD. So all these, after approval, these ADME data can really feed back to your ADME database again, right? So this process, what the process would help us a lot is in terms of using the database plus PAMPA dissolution. What that will help us out is figuring out a fairly feasible way with a shorter time, much lower risk in predicting these drug performance in after clinical study, right? So we can predict that precisely using the PAMPA dissolution. And once that formulation compare with your IOD, and that will be fairly close for these PK performance in human subject testing. Okay, so that is the idea for this NDA formulation development. Yet let's take a step back. Is that once you have your NOEL determined, you need to follow the FDA required step to figuring out the MRSD. Once you have your MRSD, the next step is you need to propose your PAD, right? So how to do that? Let's check it out. The PAD determination, you can maybe refer to such an article. That article states this way: you need your PE and CL from CACO2 and human hepatocyte determined in vitro-wise, and then you proceed simulation, ADME simulation with PBK model. You can end up with a fairly good prediction of PK. With that PK, then you can compare with this database, ADME database of the previous approval drug. So that comes back to our new drug formulation development, right? So like I said, once we done this, that's the previous PPT, we will obtain the PK. Then step 2, use that IOD, because you have the PK, use that ADME database to figuring out your IOD. Once you have your IOD selected, then you do your PAMPA dissolution. You had the curve generated from PAMPA dissolution, the permeation curve. Then you can start your formulation by comparing your formulation's permeation with respect to the IOD permeation. So then once they are fairly close, that means your formulation is done. In this way, that will save lots of your times, effort, and decrease a lot of your risk in terms of human clinical study. Okay, so it's fairly by scientific way in doing through step 1, 2, 3, and 4. In this way, that really can save scientists' efforts and really can point out fairly close to the PK that is expected, okay, for your new drug. All right. Now, the real steps is illustrated in this PPT is that you have the upper graph as we seen previously, and once you done this PK simulation compared to the ADME database, then you will have something like this, the graph, because once you compare, then you know, by compare this, you will have the, let's say one is your target, one is your reference, right? So you will have this graph generated, by literature. And then once we had these done, you can do your RLD through this PAMPA dissolution. You will end up with the graph like this. Say if your RLD is isotopic, and then your isotopic curve look like this, yet you start doing your formulation, right? Once you done your formulation, it look like this, is a bit like away from this target curve, permeation curve. So what you can do is adjust your formulation and make this curve leading to closer as possible to your IOD permeation curve, and which will giving you the reflected human like blood curve as on the left side. So by doing so, your NDA formulation can be done easily. As you can see, the isotopic curve is really the orange one, which is that one. And then, your let's say if you're doing metolazone as your target one, let's say this is your NDA, then your NDA, it needs to be, improved in order to get to the isotopic IOD. Okay, so by doing such a process, you can really doing your drug formulation in a faster and safer way, predicting your PK easily instead of guessing by this dose escalation. Okay, so that's for NDA. The other one is for 5-5B2. In case of 5-5B2, the prediction can be done using PAMPA dissolution also. Let's take a look at this case study. From injectable to oral. How can we do that? Any injectable, it has the PK data also. So you have DME, right? And this ADME data, you'll have it. However, in this case, you'll need DME data. Okay. So once you have this DME data, you can, of injectable, you can like compare with the oral database, right? And with those, let's say in these two cases, if your injectable having closer DME data to these two drugs, then your next step is try to do your this PE through KECO2 or through PAMPA. Then you are able to arrive with your permeability, right? So with internally DME and the administration for permeation data, then you can figuring out whichever closer to your needs, and then you can refer to their dose and calculate for your Cmax. Okay, so by doing so, your really your selection of the dose from injectable to oral, it will be a lot easier because they are based on human ADME process instead of like doing from guessing, So doing this way, it will be a lot faster and safer with PAMPA dissolution as a helping tool. And that will, saving a lot of your time and decreasing your research risk. All right. So that's about it for today's presentation For first one is DNA NDA. I'm sorry, for NDA and 505(b)(2) application anyway, with PAMPA Dissolution. So if you have any question, more than welcome to email me or contact me through my cell phone or email. Okay, that's it for today's presentation. Appreciate. Thank you. Bye bye.